Hello everyone, my name is Sarah White and I'm a postdoctoral fellow at Rhodes University and based in the Meerkat office in Cape Town. Thank you very much to the organisers for accepting my talk on multi-wavelength analysis of active galactic nuclei. So what exactly are active galactic nuclei? Well, we find one of these at the centre of a galaxy that has gas or material accreting onto the supermassive black hole. And as this accretion process takes place, we produce a large amount of emission over a wide wavelength range. And in about 10% of cases, we also have the production of these powerful radio jets as illustrated here. Now, another phrase I'll use in the talk is this idea of a radio core. And by this, I'm referring to the radio emission connected to the accretion disk, this whirlpool of gas close to the supermassive black hole at the center. And this accretion disk also produces optical light. But if we view the AGN from a particular angle, i.e. side on, we also encounter this dusty torus that's surrounding the accretion disk. And as a result, that optical light is obscured, but the energy can be absorbed by the dust and re-radiate in the mid-infrared. So that's another way of finding these obscured AGN. We're yet to understand these systems fully and their role in galaxy evolution. For example, how connected is black hole accretion to star formation in the galaxy? Because both of these processes appear to follow a similar trajectory over cosmic time, both peaking around redshift 2. Now, is this due to genuine interaction, or does it boil down to there being a common reservoir of gas that fuels both the star formation and black hole accretion? And there's also debate over the overall impact of radio jets on the host galaxy in terms of whether they suppress or promote star formation. And of course, with new observations, we get new questions. And here's a stunning image from Meerkat, in which we've discovered these beautiful collimated synchrotron threads. Now, how exactly did these form? And if it was an issue of limited sensitivity and limited dynamic range that prevented us from seeing these threads before, then just how common are they across the radio galaxy population? Now, radio observations are great for giving us an unbiased view of the universe, which is not possible at other wavelengths. This is because even when we have dust along the line of sight, we can still pick up star formation and black hole accretion processes. So they both contribute to the radio emission. But then the problem becomes, how do we disentangle those two contributions? And doing this carefully will prove even more important as we probe to lower radio flux densities using SKA precursors and pathfinders. As we do so, we notice a flattening in the source counts, which suggests we're moving from this AGN-dominated regime to a star formation-dominated regime. However, at these lower radio flux densities, it's not just star-forming galaxies there. As shown by simulations by Willman et al., there's also a contribution from radio-quiet AGN. So this is where my talk now splits into two parts. I'll next discuss a sample at the bright end before returning to work at the faint end. Now, this sample of the brightest radio sources in the southern sky is known as the Gleam-4-Jansky sample. And each of these sources has an integrated flux density above 4 Jansky at 151 megahertz, as measured for the Gleam extragalactic catalog, which uses data from the Murchison Wide Field Array. The vast majority of this sample are active galactic nuclei, and here we have a histogram of their radio brightness. So the sources to the right of this vertical line are the types of AGN that we're familiar with, familiar flux densities, because they are similar to the 3CR sample, which is limited to the northern hemisphere. But the Gleam-4-Jansky sample is 10 times larger, which allows us to investigate the properties and feedback mechanisms in these galaxies as a function of redshift and also as a function of environment. Now, in creating the Gleam-4-Jansky catalog, we conducted several passes of visual inspection using multi-wavelength data sets. And the key bits of information we provide in this value-added catalog is an indication of the radio morphology and, crucially, that host galaxy identification, because that's what allows us to cross-match these multi-component radio sources with information at other wavelengths. Now, this catalog is available on Visio and this GitHub repository and contains many flux densities and spectral indices. And all the nitty-gritty details are provided in paper 1, whereas paper 2 documents all of the very detailed and time-consuming literature checks that were done to ensure very high quality. I like to refer to that second paper as the Hitchhiker's Guide to the Southern Radio Sky, just because of the wide variety of radio sources that it describes. Now I'd like to emphasize why it is we use mid-infrared images for doing our host galaxy identification. So in the top left, we have an identification from 1992. This is the position shown by the cross here. And this likely came about because this was the brightest optical source close to the ridge or the neck of the radio emission between the two radio lobes. However, if we use mid-infrared images instead, this allows us to also see the dusty sources. And we can see there's a much better candidate for the host galaxy. And that's what prompts us to then go dig into the literature and see if we can find a higher resolution radio image to confirm this. And indeed, we find that the radio core has been detected and coincides with our host galaxy identification. So the higher the resolution, the better for us to be certain that we've got the right host galaxy, and all of the science that then follows is not in jeopardy. However, for some Gleam-4-Jansky sources, either the existing radio images are too low resolution to really understand the morphology, or the Gleam-4-Jansky source is in a particularly dense environment where there are many mid-infrared candidates to choose from. And those are the sources, 140 of them, that we follow up using Meerkat. And this is an excellent instrument because it has numerous short baselines for detecting that diffuse large-scale emission, but also a number of large baselines for getting us our 6 arcsecond resolution. So our sources spanned a flux density range of 4 Jansky all the way to 50 Jansky. And here are a few of the new overlays that have been produced by my master's student, Katleho Sejake. In the top left, we have a nice example of how well matched that Meerkat resolution is to the underlying mid-infrared images. Now we can unambiguously identify the host for this source and see how it's distinct from nearby candidates. The resolution also allows us, in the top right, for this source to pick out the narrow jet emanating from the supermassive black hole, and this then billows out into these large radio lobes. This resolution becomes even more valuable for the most southerly sources, which are beyond the coverage of TGSS, which is represented by the yellow contours. So for the source in the bottom right of this slide, we went from a 45 arcsecond resolution from SUMS straight to around the 7 arcsecond resolution from Meerkat. Now we can see that the radio emission is resolved into 2 tails. This is a bent tail galaxy where the jets have emanated outwards, and due to relative motion of the host galaxy with the surrounding medium, those jets and lobes become bent backwards, or the host galaxy has been subjected to intra-cluster weather. Now at this point, I changed tack from talking about radio loud AGN to talking about radio quiet. But by radio quiet, I don't mean that they're radio silent. They just have relatively low levels of radio emission. So largely the absence of these really powerful radio jets. Now we still don't understand that much about them, including their contribution to the radio background, but also what is their role in galaxy evolution. So there's been much debate over the origin of the radio emission in these objects. For the longest while, it's been assumed that star formation must dominate, just given the very low radio flux densities we're dealing with. But you could say that the debate over radio quiet AGN has been getting louder of late as more evidence builds for the accretion component. So how do we do this separation of the radio emission that's due to star formation and what's due to black hole accretion? Well, we could make use of the far infrared to radio correlation, which is represented by this diagonal line here. So this is showing where we would expect the star-forming galaxies to lie, since star-forming regions have dust that radiates, cool dust that radiates in the far infrared, but also the presence of supernova remnants giving us the radio emission. So that's where we would expect to see them. And then the degree of offset from this correlation suggests that we have a significant component that's actually due to some other process. In other words, it's connected to an AGN. Now we want to take this a step further by using larger samples and also deeper radio data. And for this, we're making use of MIGHTY, which is one of the large survey projects on Meerkat. And please do see the earlier talk by Imogen Whittam for more details. Now, my PhD student, Neo Namane, has been using the Cosmos data, the MIGHTY data for the Cosmos field, to extract radio flux densities at the positions of AGN as best fit by AGN templates using deep optical and near-infrared data. So that's the radio flux density distribution shown in the top left here. And as part of that AGN template fitting, we also get an estimate of the star formation rate, which is what's plotted along the x-axis here. And then using that radio flux density and calculating the radio luminosity, we can get a second estimate of the star formation rate if we assume that all of the radio emission is due to star formation. So we'd expect any purely star-forming objects to lie along this line. But the fact that we have this offset indicates that, yes, there is excess radio emission that can't be explained by star formation alone. There must be an AGN component also. And further investigation would be needed to explore whether there are radio jets present, but they're just too small to be resolved, or whether this is actually due to outflows connected to that accretion disk, which are impacting on the surrounding medium, creating shock fronts and generating that radio emission. So now I'll leave you on this final slide. By doing a selection at low radio frequencies, we can build up samples that are free from an orientation bias and also picks up older radio emission, so giving us a much better idea of the life cycle of an AGN. For the Glean-Forjansky sample, we used the SKA low precursor to do our selection and have followed up some of the more unusual sources using the SKA mid precursor. For a subset of the sources, we've also got an ongoing spectroscopic campaign because we want to get all of these redshifts in place to create this valuable legacy data set. And also we want to push Meerkat to its limits, going nice and deep in order to generate these large samples of radio quiet AGN. And this is important if we truly want to understand the feedback processes of AGN, whether they're radio quiet or radio loud, the whole population. And also, if we want to use faint radio sources to map the star formation history of the universe to high redshift. Thank you for listening, and I look forward to your questions.